The line pickup element that is available in the D60 is an additional protection feature that provides fast tripping of a breaker for instances where a breaker is closed onto a fault. It is also referred to as the switch onto fault function. The operation of all distance elements are blocked for a brief period after the energizing of a breaker is detected to avoid a race condition that can occur as the voltage and current builds up from a zero level to their steady states. During this period, the line pickup element will protect the transmission line. Before the line pickup protection element will be made available to protect the transmission line, it must first detect that the breaker leading into the transmission line is open. This is sometimes known as arming the line pickup element. There are two ways that the line pickup element can detect if the breaker leading into the transmission line is open. The first is by reading the status of the breaker 52B contact. If the 52B contact is wired to a contact input of the D60 and that contact input is forced on, it means that the breaker is open. The other way the element detects an open breaker is by detecting that the magnitude of the current and the magnitude of the voltage have both essentially dropped to zero. Either of these conditions will arm the line pickup element. Once the line pickup element has been armed by detecting that the breaker leading into the transmission line has been opened, there are three different ways that the line pickup element will detect that the breaker has been closed onto a fault and then signal the D60 to trip the breaker. The first method the line pickup element uses to detect a breaker closing in on a fault is by using an instantaneous overcurrent element that is built into the line pickup scheme. If the line pickup element detects that the magnitude of the current has risen above the pickup level of this IOC element, it indicates that the current is not flowing to a load but instead to a fault. Therefore, the pickup level of this element must be set higher than the maximum amount of current that will be seen during normal inrush conditions. Please note that this line pickup element is different than the normal IOC element that is available in the D60. This line pickup overcurrent element will only be used once the line pickup element has been armed. The second method the line pickup element uses to detect a breaker closing in on a fault is by first identifying that the breaker is actually closed. This is done by monitoring the status of the 52B contact or by detecting some current or voltage on the transmission line. Once the breaker being closed is established, the second criterion is that the D60 must detect a fault within its Zone 2 area of protection. Both of these conditions must be true to cause the D60 to trip. Zone 2 is used instead of Zone 1 so that we can be sure that the entire transmission line is being monitored for this fault. The third method the line pickup element uses to detect a breaker closing in on a fault is used for transmission lines that are being fed from a weak source. If the breaker is closed onto a fault on a transmission line that has a high system impedance ratio, the current will be relatively low and the voltage will be measured as essentially 0 volts. In this scenario, none of the two methods described before will pick up because of this very low current level. Therefore, for this method, the line pickup element will use the internal line pickup instantaneous overcurrent element to monitor for the presence of low current flow and no voltage. If it detects both of these criteria, it will signal the D60 to trip the breaker. Extra care must be taken when the trip output is used on weak systems such as this, because the pickup setting of the line pickup instantaneous overcurrent element needs to be set very low. Upon closing the breaker, normal inrush currents would cause this element to trip if the voltage level were slower to build up than the current. For this reason, an additional blocking delay has been added to the line pickup element that allows enough time for the voltage to rise to its steady state before the element is allowed to trip. We will now discuss all of the settings that need to be configured for the line pickup protection element to operate correctly. Before the line pickup feature can be used in the D60, it must be enabled in the function field. The source setting needs to be set to let the line pickup element know which currents and voltages to use to protect the transmission line. This setting should be set to the same source that the distance elements are using. If the transmission line you are protecting has a strong source, the phase IOC line pickup field needs to be set to the minimum amount of current that needs to be present to adhere with the first method of detecting a fault, that is, having a very high magnitude of current. This setting needs to be set higher than the maximum amount of current that will be seen during normal inrush conditions. If the transmission line you are protecting has a weak source, this phase IOC line pickup setting needs to be set low enough to detect the levels of fault current that will occur on weak systems. You will note that this setting will be lower than the normal inrush current. The undervoltage pickup setting has two purposes. This setting defines the magnitude that the voltage must be below in order for the arming of the line pickup element to occur. This setting is also used to set the maximum amount of voltage that can be present to adhere with the third method of detecting a fault that has low current levels and no voltage on a system with a weak source. This setting should be set below the minimum voltage under normal conditions. The line end open pickup delay defines the minimum amount of time the no voltage and no current condition must be present before the line end open status will be declared and the line pickup element will be armed. The line end open reset delay sets the length of time that the scheme has the ability to trip the line once it has been armed. After this time has expired, the line pickup element will be disabled until another line end open status has been identified. The over-voltage pickup delay defines the amount of time the scheme will be armed right after a normal, unfaulted breaker close. This is used to supervise the scheme on weak systems. You'll remember that for weak systems, the phase IOC line pickup setting was set below the normal inrush current level. If the line pickup element is used in this format, an extra delay is added to the operation of the element to allow the system to stabilize itself in unfaulted reclosing situations. The auto-reclose coordination bypass is normally enabled if the line pickup element is being used on weak systems and disabled if it is being used on a strong system. The auto-reclose coordination pickup delay will only be used if the auto-reclose coordination bypass setting is set to enabled. This field sets the length of time to block the line pickup element after reclosing to allow for the unfaulted system to stabilize. The auto-reclose coordination reset delay setting will specify how long the line pickup element will hold the trip output flag in the on state to ensure the breaker has enough time to complete the tripping sequence. This setting should be set to at least the breaker tripping time. The terminal open field is used to indicate to the line pickup element when the breaker is open. In this field, you will need to program which D60 input is indicating the status of the open breaker. Normally, this would be a contact input that is wired to the 52B contact of the breaker. In order to calculate the impedance of a transmission line, the D60 must measure the magnitude of the current and voltage on the line. Although the CTs and VTs are often drawn as a single instrument on single-line diagrams, in actuality, there are 3 CT inputs to the relay and 3 VT inputs to the relay, one for each phase of the transmission line. In between each VT and the D60, a fuse is located to protect the secondary devices, such as relays, from being exposed to very high voltage levels. If one or more of these fuses were to blow, the D60 would not read any voltages on that phase. Now if the D60 were to perform its impedance calculations, the equation using the phase with the blown fuse would result in an impedance of 0. This 0 impedance would fit into the D60's Zone 1 area of protection, which would then proceed to cause the breaker to trip immediately. There are 2 classes of fuse failures that can occur. The first type is when there is a loss of 1 or 2 phases of voltage due to blown fuses. This is known as a Class A fuse fail. The second class is when there is a loss of all 3 phases due to all 3 fuses blowing. This is known as a Class B fuse fail. The D60 has the ability of detecting both classes of fuse failure and can block the distance elements from tripping in both conditions. The flex logic operand that is output from the VT fuse fail logic is labeled source VT fuse fail operate. The X after the source represents the number of the source that this VT fuse fail element is protecting. This operand will turn on whenever the D60 detects that one or more of the VT fuses has blown. There is only one setting that needs to be set if the VT fuse fail feature needs to be used. Simply enable the fuse fail feature for each source you require protected. A stable power swing is a condition where a system loses synchronism for a short period of time with a neighboring system and then later regains synchronism. There are 2 reasons that a power swing such as this can occur. The first scenario is one of the systems loses a significant amount of generation, therefore instantly becomes much weaker, and the load of the system remains constant. The second is the system being already weak and the load suddenly increasing substantially. During a power swing, the voltages and currents will fluctuate significantly. This fluctuating has a drastic effect of the measured impedance of the line. The plotted impedance as measured by the D60 will slowly swing from our load point into the distance zones of protection, and then back out to a load point if the system regains synchronism. The power swing blocking feature can detect that this impedance swing is a recoverable power swing, and blocks our distance zones from operating. The D60 detects power swings by establishing an area located around the zones of protection. If the D60 detects that the impedance of the system is located in this area for an extended period of time, it knows that this is a power swing and that the distance protection needs to be blocked. If this swing were a real fault that entered the power swing blocking area, it would have moved very fast and entered the zone of protection. The impedance would not have been in the blocking zone long enough for the blocking time to expire. The power swing blocking characteristic must therefore be configured to be much larger than the distance Zone 1 area of protection to ensure a stable power swing is detected well before Zone 1's operating characteristic is reached. The D60 has power swing blocking and out-of-step tripping capabilities as part of the power swing detect function. In this course, we'll only refer to power swing blocking. There are 2 or sometimes 3 characteristic zones of the power swing blocking feature. The diagram shown here is a 2-step coordination example. The 2 zones in this diagram are the outer zone, which is the tomato shape, and the inner zone, which is the lens shape. The outer zone is what detects the power swing and sets the block of the distance element. If the impedance enters the lens shape, the power swing block stops considering this a power swing. However, it does hold the block signal on for a while to allow the impedance to leave, as will happen in a stable swing. The power swing detect function has the following settings that need to be configured for each application. In order to use the power swing detect function, the function field must be set to enabled. The source setting defines which currents and voltages will be used to detect the power swing. This setting needs to be the same as the source used for the distance zones of protection. The shape field allows you to set the power swing blocking zone to be MO-shaped or quadrilateral shaped. The mode setting lets you specify if the power swing blocking feature will be using 2-step or 3-step coordination to detect a power swing. The supervision field specifies the minimum amount of positive sequence current that must be available before the block feature will take effect. The next group of settings is used to define the shape and size of the power swing blocking zone. If the MO shape was selected in the shape field, the following settings need to be set. The power swing forward reach setting specifies the overall size of the forward reach of the blocking zone. This setting should be set higher than the sum of the transmission line and remote source positive sequence impedances. The power swing forward reach characteristic angle specifies the angle of the forward reach impedance. The angle is measured from the positive x-axis as shown here. The power swing reverse reach setting specifies the overall size of the reverse reach of the blocking zone. For a simple system consisting of a line and 2 equivalent sources, this reach will be higher than the positive sequence impedance of the local source. The power swing reverse reach characteristic angle specifies the angle of the reverse reach impedance. The angle is measured from the negative x-axis as shown here. The power swing outer limit angle defines the shape of the outer block zone characteristic. If this angle is set to greater than 90 degrees, the result will be a tomato-shaped characteristic. If the angle is set less than 90 degrees, the result will be a lens-shaped characteristic. Consideration must be taken when setting this angle to make sure the impedance, when under maximum load, will not fall into this region. The power swing middle limit angle is used for setting the shape of the middle zone in a 3-zone blocking characteristic. The power swing inner limit angle defines the shape of the inner power swing detect characteristic. The inner characteristic typically needs to be larger than our Zone 1 characteristic to ensure that power swing blocking will pick up before the impedance locus reaches Zone 1. The coordination timers need to be set to indicate how long the impedance needs to be in each zone in order for the D60 to block operation of the distance elements. Careful consideration needs to be taken to make sure that the fastest possible power swings will be detected. The power swing pickup delay timer 1 defines the time that the impedance must spend between the outer and inner characteristics in the 2-step operating mode before the power swing blocking signal is established. This time delay must be set shorter than the time period required for the impedance locus to travel between the 2 selected characteristics during the fastest expected stable power swing. The power swing reset delay 1 setting defines the dropout delay for the power swing blocking signal. When the impedance locus leaves the outer characteristic, the power swing reset delay 1 timer is started, and the block is held on until this delay expires. This setting should be selected to give extra security for the power swing blocking action. As mentioned before, Many faults that occur on transmission lines are transient in nature. That means that the fault is temporary and no repairs need to be made. Simply tripping the breaker and then after a time period reclosing the breaker is sufficient to clear the fault and bring the transmission line back into service. Historically, a separate device known as a recloser was used to perform the delay and closing of the breaker. Modern multifunctioned relays such as the D60 have this feature as a built-in element that can be used. It is known as the auto recloser. In the D60, this feature has the ability of controlling the closing of one phase of a breaker at a time or closing all of the phases simultaneously. Quite often you will see a phase that can be tripped independently referred to as a pole. For this course, only the three-phase reclosing part of the recloser will be covered. We will now describe the operation of the auto recloser and how some of the settings affect its operation. The sequence of the three-pole recloser operates as follows for a single-shot reclosing. On our example power system, the breaker is closed, the system is running as normal, and the auto recloser is enabled. At some point, a fault occurs on the protected line. This fault is then sensed by the D60. The D60 will then issue the trip command. At the same time the trip command is signaled, the auto recloser gets initiated, which starts the reclose in progress status. There will now be a brief delay until the breaker has completely opened. At this time, the auxiliary contacts will have signaled this open status to the D60. This also starts the three-pole dead time 1 timer. The actual breaker currents will finally drop down to 0 amps. The reclose in progress state remains active until the three-pole dead time 1 timer times out. Once the three-pole dead timer 1 has expired and a reclose command is issued by the D60, the shot counter is changed from 0 to 1. There will now be a delay as the breaker takes some time to close. The D60 will get an indication of the closing through its contact inputs. If the fault is still present, it will take some time for the protection algorithms to identify the fault. When the fault is identified, the D60 will again issue a trip. At the same time, an auto reclose gets initiated again, which starts the reclose in progress status. The breaker takes some time until it completely opens and signals the D60 through its auxiliary contacts. The D60 will now lock out the auto recloser. The recloser will now need to be reset before any other reclosings will be allowed. The auto reclose scheme has the following settings for each breaker that should be considered for each application. Only the settings for three-pole reclosing application for one breaker will be discussed. Set the scheme to enabled if the function should be used. Set the auto reclose mode. Here it is set to 3-pole B, which will reclose 3-pole for all shots of all kinds of faults. Set the maximum number of reclose shots to 1. Select a flex logic signal or input that will block the recloser for breaker 1. None was selected here. Set the maximum expected closing time of breaker 1. Here, 100 milliseconds was selected. Select a flex logic signal or input that will manually close breaker 1. Here, none is selected. A manual close will block the recloser. This time defines how long the recloser will be blocked for. Here it is set to 10 seconds. Select a flex logic signal or input that will initiate 3-pole reclosing. Here, virtual output 4 was selected. The breaker 3-pole open field is used to indicate the status of the breaker. Enter the flex logic signal or input that indicates the breaker status. Select the dead time from when a breaker open condition is sensed until the first reclose command is issued. Here it is selected as 1 second. The 3-pole dead time 2 field specifies the dead time for the second reclose attempt. In this case it won't be used since the maximum number of shots is selected as 1. The reset field indicates which input is used to reset the auto reclose if it is locked out. The auto reclose reset timer specifies the time from first auto reclose initiate until the auto reclose will be automatically reset after all or one shot reclosed successfully after the fault is cleared. The block field is used to block the operation of the entire auto reclose scheme. Here, virtual output 12 is the flex logic signal used to block the auto recloser. The incomplete sequence timer specifies the maximum amount of time from when the reclose was initiated to the time a successful reclose did not occur. This is used for each shot. If the timer expires, the recloser is then locked out and sets the auto reclose incomplete sequence alarm. This time should be set longer than the longest dead time plus maximum expected opening and closing times of the breaker. Throughout this course, we have shown you the theory behind most of the major protection elements that are available in the D60 and how to configure these elements. We also covered all of the output signals that these protection elements produce. Some of these were the 4-zone operate flags and the zone phase trip flags. We also demonstrated how all of the pilot schemes worked and described all of the settings that they needed configured to operate correctly. All of these pilot schemes also produced output signals. The next normal process in programming a UR platform relay would be to now take all of these output operands and develop flex logic equations to customize the relay to trip when you require it to. Since there is such a large number of these operands available in the D60 and the tripping schemes can become quite complex, programming all of this logic can become daunting. This is why the developers of the D60 have produced some pre-configured logic that eliminates the need to create your own customized flex logic equations to trip and auto-reclose the breaker. This is known as the trip output logic. Using the trip output feature, the user now only needs to enable and configure all of the distance protection elements, pilot schemes, and control elements that they want to use. All of these elements are hardwired to the trip output through the D60 internal logic. The trip output feature takes into consideration all of the possible logic that might be needed for line distance applications, such as protection elements, pilot schemes, breaker fails, and so on. Using the pre-programmed logic, the trip output now determines, based on the status of all of these inputs, whether or not the breaker should be tripped or reclosed. Once the trip output has analyzed all of the logic, it produces several outputs that should then be assigned to trip the breaker. These outputs are trip phase A, trip phase B, trip phase C, trip 3-pole, and trip 1-pole. The trip output also gives an output signal that should be used to initiate the auto-reclosing sequence of the breaker. This output is labeled Trip Auto-Reclose Initiate 3-pole. We will now discuss all of the settings that need to be configured to make the trip output element operate correctly. If you wish to use the trip output feature, you need to select in the trip mode field either 3-pole or 3-pole and 1-pole. 3-pole should be selected if you want to trip all 3 phases for all faults. 3-pole and 1-pole should be selected if you would like to have the ability of tripping only one of the phases when a single phase-to-ground fault occurs. In the next 6 fields that are labeled Trip 3-pole Inputs 1 to 6, you need to enter all of the protection element output operands that you wish to cause a 3-phase trip when they detect a fault. If you require the ability of selecting more than 6 inputs to cause a 3-phase trip, you will need to create a flex logic equation where all of those additional inputs will be ORed together and then assign that virtual output to this list. The next 6 fields that are labeled Trip 1-pole Inputs 1 to 6 are only used if the trip mode setting was set to 3-pole and 1-pole. If they are being used, you need to enter all of the protection element output operands that you want to trip only the faulted phase when a fault is detected. If single-phase tripping is configured and a single phase is tripped upon detecting a fault, this single phase will automatically be reclosed by the D60. If the fault is still present after this reclosing, all 3 phases will immediately be tripped. If you require the ability of selecting more than 6 inputs to cause a single phase trip, you will need to create a flex logic equation where all of those additional inputs will be ORed together and then assign that virtual output to this list. The next 6 fields are labeled Trip Reclose Inputs 1 to 6. In these fields, you need to enter all of the types of faults that you wish to initiate a reclose after the breaker has been tripped by that protection element. If you require the ability of selecting more than 6 inputs to initiate a reclose, you will need to create a flex logic equation where all of those additional inputs will be ORed together, and then assign that virtual output to this list. The Trip Force 3-pole field allows you to input a command to the relay to force the D60 to immediately trip all 3 phases of the breaker. Often, this is an input that allows for manual input from a user, such as a contact input or a virtual input. The Trip Pilot Priority setting is used to block the assigning of the pilot scheme output operands for a short period to make sure the communication delay will not cause any maloperations. This setting should be set to the inter-relay communication channel delay time plus some additional margin. The breaker phase A, B, and C open fields are used to indicate the status of the 3 phases of the breaker. If all 3 phases of the breaker are indicated by the same 52A input, You should assign that same input to each of these three fields. If the breaker control function is being used, these settings can be left at the defaults. We will be covering the breaker control function in the next section. Since you have already completed all of the previous sections of this training course, you are now familiar with the process of setting up all of the protection elements that are necessary to protect a transmission line. We have also shown you how to configure all of the various control functions, such as the auto recloser function that is used to automatically close a breaker after transient faults, and the trip output feature that is used to handle all of the tripping logic in the D60. The next step in programming your D60 is to take all of these control outputs and create a scheme using flex logic. This scheme will take all of these outputs along with all of the contact inputs which show the status of your breaker and create your tripping logic. However, just like the trip output scheme we discussed earlier, the D60 has a pre-configured scheme to handle all of this logic for you. It is called the breaker control element. Using the breaker control feature, the user now only needs to configure the trip output feature and the auto reclose feature. The outputs of these two elements are internally hardwired to the breaker control feature of the D60. Finally, the user must program into the breaker control scheme which D60 contact inputs are being used to monitor the status of the breaker. The breaker control scheme will take care of the rest of the logic. The output of the breaker control scheme will only be two operands. The first is called the breaker1 on command, which indicates the breaker should be closed. The second is called the breaker1 off command, which indicates the breaker should be opened. There is the ability to control two breakers with the D60, and that is why the number 1 is listed in the breaker control operand seen here. The only step the user must now perform is to assign the breaker1 on command to the contact output that closes the breaker, and assign the breaker1 off command to the contact output that trips the breaker. We will now discuss all of the settings that need to be configured to have the breaker control feature operate correctly. As for all elements in the D60, if you wish to use this feature, you must enable it in the function field. If you wish to use the push buttons on the front panel of the UR to control the breaker, the push button control field must be enabled. If you wish to rename the breaker, you can do so by typing text into the name field. The mode setting determines if the breaker will always be tripping all three phases for all faults, or will be tripping only one phase for a single phase fault. In this field, select 3-pole or 1-pole. The open field specifies the D60 input that is used to manually trip the breaker. This will also normally be a contact input, a virtual input, or the result of a flex logic equation that ORs these two inputs together. The close field specifies the D60 input that is used to manually close the breaker. This will normally be a contact input, a virtual input, or the result of a flex logic equation that ORs these two inputs together. The next three fields are used to indicate the state of the breaker to the breaker control function. If 3-pole tripping is used, only use the field labeled phase A/3-pole. In this field, select the contact input that is wired to the breaker 52A auxiliary contact. If single-phase tripping is being used, the status of each phase of the breaker needs to be indicated in the corresponding fields. The external alarm field lets the breaker know if any alarms, such as a low-pressure gauge, have been detected. This field will normally be a contact input wired to the alarm signal. The alarm delay field indicates the length of time the alarm must be on before it will be acknowledged by the breaker control feature. The manual close recall time specifies the minimum amount of time that the close signal will be held on to be sure that the breaker has enough time to close. The out-of-service inputs tells the breaker control feature when the breaker is unavailable for tripping or closing for any reason. The following settings are all used for an advanced function of the UCA2 communications protocol and will not be covered. In the few final sections of this learning CD, we will give an example of how to set up and configure all of the control and protection elements we have just described, including the line pickup element, the power swing blocking element, the VT fuse fail function, the breaker control element, and the auto recloser. Finally, we will assign the outputs of these functions to the contact outputs to complete all of the settings necessary for our D60 transmission application. In the settings file used previously, open Grouped Elements, Group 1, Line Pickup menu. Set the function field to Enabled to make this element active. Keep the signal source setting as Source 1, which is the same source as the distance elements. Keep the phase instantaneous overcurrent setting at 1 per unit and the undervoltage pickup setting at 0.7 per unit. These are realistic values for a system with a system impedance ratio of less than 30. Also, keep the line end open pickup delay as 150 milliseconds and the line end open reset delay as 90 milliseconds. This ensures that the line end open will be set well after the breaker has opened and will remain sealed in long enough for the line pickup to operate properly. Leave the overvoltage pickup delay at 40 milliseconds to ensure this will pick up after the breaker has closed. The auto reclose coordination bypass can be enabled since our transmission line is supplied by a strong source. The two auto reclose coordination timers will thus not be used and can be disregarded. Change the terminal open field to flex logic signal breaker 1 open, which is the signal from the breaker control logic. This signal indicates the breaker is open from the breaker 52A contact. This will be set a little later in the breaker control menu. The block function won't be used for this example and can be left as off. Change the target to latched and the events to enabled to have the operating of this element appear in the event report. Then save these settings to the settings file and close this window. We will now configure the power swing blocking element. Go to Grouped Elements, Group 1, Power Swing Detect. Enable the scheme by setting the function field to Enabled. Keep the signal source setting as Source 1, which is the same as the source used by the distance element. For this example, we'll use the Mo shape with 2 steps, so keep shape as Mo shape and the mode field as 2-step, since we're only going to use the power swing blocking function. Keep the current supervision field at 0.6 per unit, since the currents will be much larger during a power swing. For the reach settings, we'll assume the source impedances of the local and remote ends of the line to be equivalent to the line impedance. From example 1, the positive sequence impedance is 38.7 ohms at an angle of 79 degrees. Therefore, set the forward reach to the line impedance plus the remote source impedance, which is 77.4 ohms. The next 2 quad settings can be disregarded since we're using the Mo shape. Set the forward reach characteristic angle to 79 degrees. Set the reverse reach to the reverse source impedance, which is 38.7 ohms. Set the reverse reach characteristic angle also to 79 degrees. Since none of the power swing characteristics are known, we'll leave the outer and inner limit angles as 120 degrees and 60 degrees respectively. Also, leave the delay 1 pickup at 30 milliseconds and delay 1 reset at 50 milliseconds. All the other timers are for out-of-step tripping only and won't be used. Save these settings to the settings file and close this window. Now we'll enable the VT fuse fail function. Go to Control Elements, Monitoring Elements, VT fuse fail menu. The only setting available is to enable or disable the function. Enable the VT fuse fail function by changing this field to Enabled. Then save these settings to the settings file and close this window. The next function we will set up is the breaker control element. However, this element uses many contact inputs to validate the status of the breaker. Therefore, before creating the remainder of the settings, let's label the contact inputs and outputs that will be used. Go to Inputs Outputs, Contact Inputs. Change the name of contact H7C to Circuit Breaker 52A, which is our breaker status. Set the Events field to Enabled. Change the name of H8C to Auto Reclose Enabled, which will enable the recloser function. Set the Events field to Enabled. Change contact M7A to circuit breaker ready, which is an indication that the breaker is ready. Set the events field to enabled. Change contact H8A to circuit breaker open, indicating the breaker is open. And enable events. Change the name of contact M7C to breaker low pressure, indicating low pressure in the breaker, and enable events. Change the name of contact M8A to manual close, indicating a manual close command, and enable events. Then save these settings to the settings file and close this window. Now we'll configure the breaker control element. Go to System Setup, Breakers. Enable the function for breaker 1 by changing the function field to enabled. No push-button control will be used, so leave this field to disabled. Keep the name as breaker 1. Keep the mode setting as 3-pole, since we're only going to do 3-pole tripping for all faults. For this example, contact input M8A will be used for a manual close. No inputs are available to manually open the breaker, so keep the open setting as off, and change the close field to contact input M8A. Additionally, the circuit breaker open signal 52A will be wired to contact input H7C. This will be used by the breaker control to read the status of the breaker. Therefore, set phase A3 pole to contact input H7C on. Phase B and phase C settings won't be used since we will always be tripping all 3 poles of our breaker. For this example, an external alarm, breaker SF6 low pressure, is wired to contact input M7C. Therefore, set the external alarm field to contact input M7C on. The contact input already has a debounce time of 2 milliseconds, so the alarm delay can be left as 0 seconds. A circuit breaker ready signal is wired to contact input M7A. When this signal is off, meaning the breaker is not ready, or when a breaker SF6 low pressure alarm is received, the breaker can be considered to be out of service, so we'll have to create this signal in FlexLogic. Open the FlexLogic equation editor under the FlexLogic menu. In the first line of our new equation, select Contact Inputs On and Breaker Low Preset On in the syntax of the next line. In the next line, select Contact Inputs Off in the type field and select CB Ready Off or M7A in the syntax field. Then OR these two signals together. And write them to virtual output 4. Save these settings and close the window. Go back to the breaker control menu, then set Out of Service to Virtual Output 4 on. The other settings are for detailed applications using UCA communications protocol and won't be used. Save these settings to the settings file and close this window. Now we'll configure the trip output function settings. Go to Control Elements, Trip Output. Change the trip mode field to 3-pole only, since only 3-pole tripping will be used in our application. In the trip 3-pole input fields, we need to set all the different reasons we would like to trip all 3 phases of the breaker. In the Input 1 field, select Phase Trips, or Virtual Output 3, which was created in Example 2. This signal will turn on if any of the phase distance zones operate. Select Ground Trips, or Virtual Output 2 for Input 2. This signal was also created in Example 2 and will turn on if any ground distance zones operate. Select PUTT Operate for Input 3 to ensure a 3-pole trip occurs for a PUTT scheme operation. The line pickup output is pre-configured inside the trip output scheme and does not need to be selected here. Since we are never tripping just one phase of the breaker, no trip 1-pole inputs need to be set. For our example, we only want to reclose upon faults that trip instantaneously and may be transient in nature. Therefore, we only want to reclose after the operation of a phase or ground distance zone 1 trip or a PUTT scheme operation. Therefore, select the Trip Reclose Input 1 as Phase Distance Zone 1 Operate. Select Ground Trips or Virtual Output 2 for Input 2. This signal was also created in Example 2 and will turn on if any ground distance zones operate. Select PUTT Operate for Input 3 to ensure a 3-pole trip occurs for a PUTT scheme operation. The trip pilot priority can be left as 0 seconds. The breaker status inputs were configured in the breaker control function and therefore do not need to be assigned here. Enable the trip event field so that the trip output operation shows up in the event record. Save these settings to the file and close this window. Now we'll configure the Auto Recloser scheme. Go to Control Elements, Auto Reclose 1P. Enable the scheme by changing the function field to Enabled. Change the Mode field to 3-pole B, since only 3-pole tripping will be used in our application. Set the maximum number of shots to 1 for a 1-shot reclose. The Block Breaker 1 field won't be used and should be left as off. The default close time for breaker 1 of 100 milliseconds is realistic for our 138 kilovolt breakers, so can be left as is. The breaker manual close can be left as off, since the manual closing is done in the breaker control function. The block time upon manual close can also be left as 10 seconds. This means the auto recloser will be blocked for 10 seconds after a manual close. The recloser is initiated from the trip output function, so no assignment is needed for 3-pole initiation. Since we are only using one recloser shot and the breaker status will be read by the breaker control function, the next few settings won't be needed. Set the 3-pole dead time to 1 second, representing the dead time before the first reclose shot will commence. The 3-pole dead time 2, the dead time extender, and the reset won't be used for this example. Change the reset time to 10 seconds, which is more realistic for our 1-shot reclose of 1 second. We now need to block the recloser if the auto reclose enabled contact input signal is off. Therefore, set the block field to Auto Reclose Enabled Off, or H8C. The only other setting needed is to set Event to Enabled. Then save these settings to the Settings file and close this window. The last settings that need to be configured are to assign the proper signals to the output contacts for tripping. Go to Inputs Outputs, Contact Outputs menu. Change the operate signals for both H1 and H2 to breaker 1 off command. This is the tripping signal from the breaker control logic. Change the name of H3 to Close Breaker 1, since this contact will be used for closing and reclosing the breaker. Change the operate signal of this breaker to breaker 1 on command. This is the close command from the breaker control function. Save these settings and close the window. Now, all of the settings necessary to put our example D60 relay into service have been completed.